Good morning, everyone. Those who are joining this call today. It's First of all, a very warm welcome to all of you, and hope you're all having a great beginning to 2025. On behalf of ACM India Council, let me take this opportunity to wish you all a very happy new year. And it's our privilege to start this first webinar of 2025 on a very, very topical subject, which is the hardware platform for Agentic AI. The specific title is SN40L, Reconfigurable Dataflow Unit. To walk us through this session, it's my privilege to introduce Dr. Raghu Prabhakar. Dr. Raghu is the founding engineer and senior architect at Sambanova Systems. His expertise is in the area of hardware architecture and compilers for data flow architecture. He has contributed significantly to 4 generations of data flow processor at Sambanova Systems. Most notably, these are called the Reconfigurable Dataflow Unit. Raghu is a holder of more than 25 patents and has extensively published in several reputed journals and conferences. Most notably, his research has been in the top 12 pick in computer architecture, picked by IEEE Micro in the year 2017. Raghu earned his bachelor's degree in engineering from PVC Bangalore, his master's from UCLA, and his PhD from Stanford University, all in the area of computer science. It's indeed a privilege to have Raghu kickstart 2025 with his this interesting webinar. So welcome again, Raghu, and over to you.
Thank you, Professor. Thank you. This is a great opportunity. Thank you for extending it. I'm really happy to be here. So let me go ahead and share my screen. So in case it doesn't show up, please let me know. All right. Okay. So okay, thank you. So yeah, as was specified in the introduction, so my name is Raghu Prabhakar. I work at Sambanova Systems, which is a AI hardware company based in the San Francisco Bay Area. And the talk will be about what does it take to accelerate agentic AI. So we'll get into some of the details, some of the basics on what I mean by agentic AI, and what are some of the fundamentals. What does it take to accelerate it? What are the issues in the current systems, and what is our approach to addressing some of these things? So this was already mentioned. This is just who I am. I've been with the company and the company's around for 7 years. So I was fortunate enough to be part of the founding engineering team. I have published papers on data flow architectures, and in the company, I do computer architecture. So I work on the data flow unit architecture itself and on the compiler. So it's the co-design between the hardware and software that I'm mostly involved in. I got my PhD from Stanford, my master's from UCLA, and my BE from RV College of Engineering, Bangalore. So this is the broad agenda for today. So I'll spend some time, maybe the first call it 10 to 15 minutes, just going through some background material. So it of course, there's a lot of resources on pretty much anything I'm going to talk about today, but I'll try to give a quick refresher, a primer on some of the topics relevant to this talk, and then I'll get into where are the issues that this talk is going to be more relevant for. Just one word of caution, I am not an ML person, so my description of the ML concepts here is going to be very superficial, and I'll be diving into the systems aspects of what does it take to bring these models up and execute them, and what challenges arise from that. So let's start with the background. So the title of the slide is saying Agentic AI is here, but let me first define what I mean by Agentic AI. So we certainly see, if you Google for these terms, there is a lot of blogs, people talking about it, opinions on what these are. But in a very simple way, the way I define agentic AI is when a system of one or more machine learning models come together to accomplish a complicated task. So that's what I mean by agentic AI. So here, every machine learning model is effectively acting as an agent inside sort of an overall system, and the overall system is architected to perform a certain task. So with that in mind, what we are seeing is, if we look at the past, call it 5 years or so, there was a window of time where, in 2017, we had the transformer architecture, which was released, and that transformed the space of machine learning. So it centralized, prior to that, there was a lot of research on what kind of model architecture makes more sense. So there was a wide variety where different researchers came up with different ideas, different ways to train, different ways to converge. When Transformer came along, in a way, it kind of centralized the core ideas in one architecture, such that it can be applicable to a broad variety of domains. So that was like an inflection point that changed how the field works. Now we are seeing another such inflection point. And that is because of the existence of very powerful open source models. So what I mean by that is, companies like Meta, DeepSeek, and other companies, they are training these transformer-based architecture models. They're training Llama. Llama is from Meta. Gemma is another model like that. They're training these models on a vast amount of data, like trillions and trillions of words, pretty much the entire data sets available, all the data available on the internet. So all recorded text history. So they've trained it on thousands of GPUs, and the resulting models, which is the model architecture and the model weights, they have been uploaded such that anybody can use it for free. And these are extremely powerful models. It's very hard for smaller companies or smaller academic institutions to recreate this amount of sort of quality. But by putting it out there in open source, it has unlocked researchers to do something more useful with it. And what this graph is showing is, okay, what are people doing with it? So this is a span of, if you look at the x-axis, that's a 3-month window. And in 3 months, if you look at the y-axis, it's going all the way up to 2,500. So 15th of July is roughly when Llama 3.1 was released by Facebook, by Meta. And in 3 months, there were about 2,500 different variations of that same model. Same thing for the other architectures as well. So if you look at what are people doing, like, what are these variations? These variations are nothing but the same model, but they've been fine-tuned on a specific expertise. So there's a model that is very good only at coding, only at the legal domain, only at certain languages, only on data which is belonging to a certain geographic domain. We've seen, I've included a couple of references as an example. We built one ourselves in the company, but that's the overall trend where there are smaller models. When those smaller models are trained and specialized to a specific domain, they do extremely well. They outperform what used to be much larger models in the past. So the more interesting thing that the ML practitioners and researchers are trying is, instead of using one giant model to accomplish tasks like translation, automatic code writing, drafting essays, maybe you can have a collection of many, many smaller models. The advantage with the collection is you can independently improve them, debug them. Doing the same amount of work takes a fraction of the cost. So this is an inflection point where we're going to see a lot more work in that area. It's not going to be just one model. It's going to be several models that are acting in some concert to accomplish a certain task. So before we go into agentic itself, I want to go even behind, saying, what does one model do? When we're saying there's a transformer, these models can generate tokens, they can generate text, they can generate code. How exactly does that work? So what are the steps involved there? So I'll briefly step through. Some of this might be knowledge to folks on this call, and for some it might be new. So I'll just step through this real quick, and then we'll connect this back into the agentic workflow and all that.
Raghu, if I may interrupt for a minute, just
Yes.
for the attendees, if you have any questions, please use the Q&A panel to type your questions. We'll take questions one at a time whenever appropriate. Sorry for the interruption. Go ahead.
No problem. So yeah, so this slide is talking about what is called autoregressive decoding. So what this just means is when you take any transformer model architecture, a transformer model is fundamentally a tokens in, tokens out model, which means given a set of input tokens where a token can correspond to a sequence of characters. For simplicity in this talk, let's assume that one token is a word. Normally it can be less than a word, it could be multiple words combined. But let's assume for the sake of simplicity that a token is a word. A transformer architecture takes a sequence of tokens as input, and then it predicts what should be the next token, provided the input tokens. So it outputs one new token at the end of execution of a model. If you want to continuously produce tokens, you take the output, you concatenate it with the original input, and you run it again. That'll produce one more word. And you keep doing this. And this process is what is called decoding. And because every token or every output word is dependent on all the previous words, it's called autoregressive decoding. That's the terminology used. So this set of slides is going to just animate it and show what's happening. So let's pretend that we logged into ChatGPT or any of these chatbots, and we just typed in once upon a time. Now remember, these models have been trained on tons and tons of text, which means given any sequence of words, it is going to generate a probability for every word that it knows. It's like, okay, what is the highest probability word that I should select? So in this example, let's say we gave an input of once upon a time, we ran the model, and it output a token, which is a comma. But then we do it again. So to do it again, what does that mean? We take the same set of tokens and we concatenate it with the result token. And then we run it again. That produces another token, say, there. And this time we do it again. Again, this time we have to concatenate the two produced output tokens and with the original input and run it once more. You get one more token called was. And we do it again. We got an A, a boy, so on and so forth. So if you keep doing, this is just a simple example. So what happened here is when you run the model 10 times, so each blue box in this picture is depicting the execution of the model. And we ran the model 10 times. And as an example, if you see the box says 70B, what that's referring to is I'm assuming that we're running a model which is having 70 billion parameters. So let's pretend that you ran the model 10 times. This model will generate 10 tokens. So that's what you see at the bottom. Just once upon a time, there was a boy who sat. You can keep going. This is pretty much the crux of how tokens are produced from a language model. So where this talk is going to go next from here is, there is a lot of reasons for us to make this token generation as fast as possible. So we'll sort of dissect each one of these things. So when you ran one of these blue boxes, one of the 70 billion parameters, what is inside of it? And what is it that takes so much time to run? What are the optimizations people are considering? What are the inefficiencies? And first of all, why do you even need to run this so fast? Because if it's a chatbot, humans can't read, if this model produces 1,000 words in 1 second, a human cannot read 1,000 words. But on the other hand, a human reading it is just one very specific use case of these models. There are several other use cases where a model can reason with itself. So this is where the agentic workflow comes back in. So when the output of a model is being fed to the input of another model or back into itself, that's what we call chain of thought reasoning. when you keep doing that, your model now needs to produce a lot of tokens. And if that token generation is quite slow, then some interesting use cases that we see today, we can use today, would not have been possible. So I'll give you one simple example of that. So this one is from a blog post that is released by OpenAI. And this is a concept called test time scaling. So simply put, there's a blog post that I've linked at the bottom of the slide. So please feel free to click that and read it when you have time. But test time scaling, simply put, is saying that you can, a large language model can perform complex reasoning tasks only at inference time. And here inference means producing the tokens, like what we saw in the previous slide. It can perform complex reasoning tasks at inference by using multiple intermediate steps. So what I mean by that is, assume that you have a language model and you're going to ask the model a question saying, how many R's are there in the strawberry? What you will eventually end up asking the model is, there'll be one prompt that says, hey, here is a question. What do you think? The model is going to produce some tokens as a response. These tokens are then fed back as input into the model with another question saying, can you explain your reasoning? Why did you say this? The model is going to produce some more tokens in response. Then you go back and forth again and again. Of course, all this is automated. It's not visible to the user. But you can see that the model is running like several times. It's producing a lot of this intermediate results before the final result. So each token in the intermediate results is going to go through the process I described earlier. So that's one of the reasons why you can producing tokens at high efficiency is extremely important to unlock the next level of sort of AI ML innovation. This slide is just saying that OpenAI is making a statement saying there are two ways to improve accuracy when you're judging the quality of a model. There are two ways to improve the accuracy on these standardized benchmarks. One is by training. You train the model with different data and you increase the accuracy. That's train time compute. That's the left side graph. The right side graph is saying you can also do this with test time compute, which is what I just described. So you can keep going back and forth by having this complicated sort of chain of thought reasoning style approach. And you will still pass the same questions. You'll still do better at the same benchmarks. And the fundamental reason behind this is what I said earlier, which is these models have seen pretty much all the data on the internet. So they are extremely capable. And the goal has been, how do you unlock that capability using these kinds of prompt techniques? So this is what I mean by test time scaling. So the fact that tokens have to be produced very quickly is not lost on people. So there's a lot of optimizations that have been deployed. I want to draw attention to one standard optimization. That's the final piece of background material that I want to go through. And that is called speculative decoding. So what do I mean here? So if I go back 2 slides. So here, in order to produce 10 tokens, I had to run a 70 billion model 10 times. So that means the time to produce 10 tokens is the time to run 70 billion model 10 times. It's as simple as that. But running a 70 billion model 10 times might not be the fastest way to do things. So speculative decoding is an idea where you don't run 70 billion model. You kind of offload to a deputy or a draft model, where the draft model is a much smaller model. Think like a 1 billion, a 3 billion, or an 8 billion model. Now, this model may or may not produce the correct result. Like, you don't want to compromise on the quality. So this model may or may not produce the correct result. So you want to run the target model every once in a while, such that it can check, saying, if I had run with this input, what would I have produced? And anytime where there is a mistake, you correct and you go back. So this is what is the basic idea behind speculative decoding. So let's just flip through that again, just to make sure the concept is clear. So if we start with once upon a time, same prompt as before. And let's say instead of running the blue model, which is the 70 billion model, I'm going to pick a much smaller, inferior model, which is like a 10 times smaller, like 7 or 1 billion model. So I will, let's say this, in this case, the draft, that's what I'm calling as the draft that produces a comma, and then we keep doing the autoregressive step. And after the few steps, the draft model produces these tokens. It says there was a girl. If you remember, in the first example, it said there was a boy. That's what 70 billion would have produced. And as a user, you don't want to compromise on what the 70 billion output is. You want that exact output. So in this case, let's say after 5 runs, we run the target model once. So this target model acts as a checker. So it checks what tokens that the draft has produced, and it produces this score saying, okay, the first 4 tokens is what I would have produced as well, but the 5th one is wrong. And instead of this, I would have produced boy. So at the end of this step, where it's a sequence of draft and 1 target model, we end up selecting these tokens. So 4 from the target, 4 from the draft, and 1 from the target. So this step, what you see on the top in one row, which is the red and the blue boxes, is called one step. Producing tokens happens in multiple steps like this. So step 1 kind of looks the same. And let's say in this example, the draft model said, once upon a time, there was a boy who sat on a box. If you remember, the target model had completely produced something else, right? So the target model says, I would have also produced who and sat, but I would not have said on. I would have said, next instead of on. So only these 2 are selected and everything else is ignored. So the advantage with this is that even though the draft model can be wrong occasionally, running the draft or the red box is so simple and it's so cheap that it is okay to do this. So there are some terms here saying there's something called an acceptance rate, meaning what is the fraction of the draft model tokens that got accepted. So in this example, in all, there were 6 tokens produced, 5 from the draft and 1 from the target, but only 4 of them got accepted. So the acceptance rate is defined as 4 out of 6. So similarly here, the acceptance rate is defined as 2 over 6. So let me pause here for a bit and see if there's any questions.
Prabhu, there are no questions from the attendees, but I have one question. So the input that is given to the 70 billion model after X number of tokens have been generated by the draft model, do you feed that entire input that has been generated by the draft model, or do you take a snapshot of what happened before the draft model got kicked off?
You take the corrected snippet. So as shown here, so step 0, in this step, for every step, you take the input at like the golden input that has been blessed and all the tokens produced by the draft. But once you run the target, you know the true sequence. And here the true sequence is, once upon a time, there was a boy. So in the next step, you start with all of these tokens again.
Okay.
And then you produce the same thing. Yeah.
So the draft has to be blessed only after whatever is output from the draft. If it is blessed, only then you continue forward.
Correct. Yeah.
Okay.
Exactly.
There's we have one question. Yeah. If
Yes,
there is no
please.
wrong term, then there is no problem. But if there is any wrong input, then the decoding will stop or not.
I'm not sure what you mean by wrong input, but let me just answer what I think you're asking. So let's say in this example, once upon a time there was a boy, the first word was wrong. So which is instead of who, let's say it was where or something like that. We, in the process of decoding, we will still run the draft 5 times, because when we run the draft only once, we don't know if it's right or wrong. We will only know if it's right or wrong at the end when we run this target model. So in this example, it will still end up producing, where, wrong token, wrong token, wrong token, wrong token. And when the target checks, it will say that the very first token is wrong, in which case all of the draft model's work is discarded, and only the target model's token is accepted. In which case, the acceptance rate would only be 1, would be 0. Like none of the draft performed horribly and there's no benefit from it. I don't know if that answered the question, but there's more. Go ahead, sorry.
No, there are no other questions. So
Okay.
I hope it did answer. If not, the questioner can again ask for further clarifications if required. Please continue.
Okay. So this is actually a very interesting design space, because as you can see, by no means is this the only way to do things. So, for example, one question is, why did I stop at 5? Like, why not four runs of draft and 1 run of target? Why not 10 runs of the draft? Does draft model do well in one domain? It doesn't do well in some other domain. I mean, all of these are valid questions, and in fact, we've studied this a little bit. So one terminology that I wanted to introduce is there's this in literature, somehow the letter K is used for speculation window. So K is basically referring to how many times you run the draft model. So in this example, K is equal to 5. So we actually computed this acceptance rates and all that. And one of the things we see is that the draft model and the target model, there are so many degrees of freedom here. So one is between a 1 billion and a 70 billion draft and target, 8 and 70, 1.5, 72, different window sizes, different data sets. How does the acceptance rate look? What does the acceptance rate look like? So the differences here is that alpaca eval is more of a generalist data set. So this is where you can have prompts ranging from literature to history to law to coding, mathematics. It's kind of a fairly general overall coverage. So this is in some sense like a harder thing for speculative decoding to do well at. Human eval is mostly a coding data set, and you can see that it does models tend to do very well on coding for speculative decoding. And GSM 8K stands for Grade School Math 8K. And this is more of a complex reasoning test, because you're supposed to solve mathematical problems with steps. So they do well here as well. So just FYI saying that there is an immense degree of, this is a very hot research topic of speculative decoding, what works well, where, why, can you squeeze out any performance here? So excellent area to work in. But let me switch gears and let's say let's zoom into one of these topics. Saying, okay, let's say K equal to 9.
Sorry to interrupt. There's one question, maybe just related, so you may want to just clarify. So the question is, can you clarify why we're using drafts and not the complete module? So we want to just clarify that again for the audience again.
Yes. So the reason for using the draft is that running this draft is a lot cheaper than running the target. So by cheaper, what I mean is, let's say that executing this target takes about 1 millisecond, meaning you have to run, one token is taking 1 millisecond. Well, one is too small. Maybe let's say 10 milliseconds to run. Producing one output word will take 10 milliseconds, which means to produce 10 words, you will take 100 milliseconds. If you run the draft model, that probably can produce a word in 1 millisecond. So the net thing is that by running draft for some time and target only lesser number of times, you can actually produce more aggregate output tokens in the same amount of time. So I'll actually show some data on this. And I think this dovetails quite well into what are the problems. Like, this is the intent, what is actually happening on GPUs, which is where that's the de facto hardware on which all of these things run, what's happening on them. Let me switch gears and say, okay, well, let's pick this row and we'll kind of zoom into it in a bit. The key thing to take away if you change your frame of reference to, as if you are the hardware vendor and your intent is to provide a platform where these models can run as efficiently as possible, with the knowledge that people are doing, agentic workloads, speculative decoding, producing a lot of tokens. What are the problems? So I've boiled it down to two problems. So one problem is that the GPUs, which is the current state of the art AI hardware, they execute these small, like the draft models, inefficiently. So there's a lot of these overheads. We'll zoom into what those are. And the second problem is, as an AI cloud or infrastructure provider, you're almost never dealing with one model. So we saw in the very first slide that the orange line was continuing to grow. And as an infrastructure provider, we would have to host and serve all of these models because customers from all over the world can query any model. So which means these models are constantly switching in and out of the GPU based on the patterns and the popularity based on traffic. So we need to be able to quickly switch between the models without incurring a significant cost. So these are the two problems. We'll zoom into each one of them independently. So first problem. So I said GPUs execute small models inefficiently. So what does that actually mean? Let's take an example. So here, small model is that red draft model that we talked about. As an example, this is data from it's measured. It's also independently documented by a third-party analysis tool called Artificial Analysis. So there's a link at the bottom where you can go check. It's a really cool website. If people don't know what it is, there's a lot of detailed insights into different providers, different models, how well they perform, where they are. Sambanova is on there as well. So the main idea behind this is when you produce an output token, given a sequence of input tokens, the operation that you perform is fundamentally communication dominated. So what I mean by that is to perform a required number of sort of computations to produce the token, you have to stream in, you have to load in some data from some memory off chip. GPUs have something called HBM, high bandwidth memory. So you have to stream data from HBM onto the chip, perform some computation, and store the results back. The amount of computation you perform on chip relative to the amount of data transferred from HBM to the chip, the compute is much, much smaller. So you have to transfer a lot of data for very little compute. So that's just inherently the nature of the benchmark or the model. There's nothing GPUs or anybody can do about it. Which means the best you can possibly do on these models is run at the peak bandwidth that your HBM provides. So if we put this into numbers, right? So an 8 billion model has about 14 or 15 gigabytes of weights and about 5.5 gigabytes of KV cache. So for those of you who know what KV cache is, hopefully I don't have to explain this, but for the ones who don't know, think of this as some latent state that the model has as you produce tokens. So in the autoregressive decoding, you would have computed some attention scores for the previous tokens produced. Instead of recomputing them again and again, you would have stored it. So which means to produce the next token, you need the weights of the model, which is around 15 gigabytes, and you need about half a gigabyte of the shared state, which is the KV cache. Which means you have to stream or load 15.4 gigabytes of bytes in order to produce one token. So this is the bandwidth available on NVIDIA DGX H100. So if you combine the bandwidth across 8 GPUs in a box, this is what you get, 24. So if the entirety of 24 terabytes per second was in use, because it was memory bound, then how much time would it take to stream 15.4 gigabytes with this time? Right? That is the amount of time. So if you just divide this, you're going to get the time, which is seconds per token. So how much time do you take to produce one output token? So if you invert that, it's tokens per second. So that's what this number is. So if we were using all the bandwidth available on NVIDIA's DGX H100, we would have been at around 1596 tokens per second. That should have been the performance. But what we have observed, this is something that we have also reproduced independently locally. This is also what other third-party providers have documented. It's there in this link as well. the measured throughput is around 300 tokens per second. Right? So 300 tokens per second is about 19% of 1596. So this is saying that when you run a small model on a GPU, you are utilizing only 19% of the net HBM bandwidth. 19% is not good. So which means you're leaving 5 times performance on the table. So why does that matter? I think this probably answers one of the questions that we talked about earlier, that was asked earlier. When we produce, if you take one step, which is some number of draft runs and the target run, how much time is actually spent in the draft versus how much time is spent in the draft versus in the target model. If you just add them up, so it does not matter what the acceptance rate is, you still have to run the draft and target same amount of time. So when we do this, we see that on the GPU, with that number that I mentioned earlier, the draft model is overwhelmingly consuming the most majority of the time. Right. So 83% of the total time per step is going in the small model in this configuration. And the target model is consuming the other 17%. So spoiler alert, on the platform that I'm going to be talking about, this number becomes much lower. So that's the, that's the punchline. I'm sort of jumping to the conclusion a bit, but how do we get there? So that's going to be the remainder of the talk. The other problem before we get there is, I said we have all these models, you have to have high, these models have to be hosted somewhere, you need to be able to switch at random. The issue is that on GPUs have HBM, and HBM only is about a few gigabytes of capacity. When you have so many models, KV caches and all these for so many models, you need a lot of memory capacity. So if the common solution used here is just use more GPUs. As you have more and more machines, you have more capacity, and hence you can spread the load across many machines. The problem is that's extremely expensive. If you're buying machines just because of capacity reasons and they are not getting utilized, then that's not good for the perf TCO, performance total cost of ownership. Because you paid for the machines, but they are not generating any revenue, so that's not good. On the other hand, if we end up using something like a disk or a CPU memory, then we'll keep swapping on demand. We'll copy it from CPU or disk into the GPU memory when it's required and back. The time taken, in executing the model is only this orange bar. The rest of the time is the copying overhead. So you really don't want the blue bar at all. We should not be wasting time copying or switching that much. We should be spending all our time in the orange bar, which is execution. Because any switching means the model, the hardware is idle, and idle is bad. All right. So how do we improve this? So we'll zoom a little bit into some of the details even further. So we said small model doesn't run very well, and the model switching. So, okay, why does the small model not run very well? So what is in a small model? We'll go one more level further. So this is the structure of any transformer architecture. I just have chosen the 8 billion llama as an example. So these are the high level blocks. So there is an embedding block at the beginning, and there's classifier at the end. The sampling block at the very end is not really part of the model, but since we do it for every token, I've just included it because it does consume time. And bulk of the work is in those orange boxes in the middle, which is what is called decoders. And these blocks are identical. It is repeating structure that happens 31 times, where every decoder takes the output from the previous decoder, does some computation on it, and produces the next output. So the end of this is the output token. So let's look at the decoder for a minute. So what is inside the decoder? These are all the operations. Right? So if you take an input that's coming in, let's call it x of d minus 1. There is a normalization. There is a bunch of matrix multiplies. This block in the middle is the attention layer, all the way from the QK to the PV. There is another matrix multiply, a projection matrix multiply, another normalization. There are 3 feed-forward matrix multiplies. skip connection. And because these things are generally mapped on multiple chips, these chips all end up producing temporary results at different points in time. And these temporary results need to all be added up and then distributed to all the other chips. So that's where these other blocks, these all reduced blocks come in. So this is the structure. This is the repeating structure. So you're doing the same computation 32 times for this model. So if we look at how the GPUs do it, GPUs execute work in quantums called kernels. So kernel is basically a function call that runs on a GPU. And when we profiled this using TensorRT LLM, this is what we saw. So it's not the only way to run it on GPUs, but that's what we observed. So this whole decoder runs as, RMS norm is one kernel, the other matrix multiplies are one kernel, attention is one kernel, projection is one, all reduce is one, again, normalization is one more, these two gems are one, so on and so forth. So you can see that one kernel can constitute one op or more than one op. And whenever there is more than one op, that's what we call as a fused operation. So there is some intelligence built into the software where multiple operations are executed together on the GPU. Main advantage with that is you don't incur additional overheads. Once you launch, you do everything and then you come back. So it ends up being more cheaper or more efficient. But the issue is that if you observe these green boxes, every time you cross this boundary, so every time you finish one green box and begin another green box, there is a synchronization cost. So imagine every green box is being executed by 8 or 16 GPUs. How do we know that that green box is finished and the next green box can begin? So they all have to synchronize, saying, okay, are you done? Are you done? So you sort of wait, and then you start the next one. So why do we need to wait? Because the next kernel is going to expect that the data is in HBM. So some guarantee has to be there that the memory, the output of the first function call is there. And this synchronization of sort of waiting at the boundaries of these kernels can cause a lot of overhead. That's what I'm calling here as there is low operator fusion, and then there is some launch and synchronization overheads. So what does that mean? So when we look at the data, so let's look at these two graphs first. If we look at the tokens per second, which is this y-axis, we did this experiment saying, let's just use 2 GPUs and then 4 GPUs and 8 GPUs. So at 2 GPUs, it's not so bad actually. So it's, you're using 50, 60% of the GPU bandwidth, not so bad. But as we add 4, 8, as we add more and more GPUs, the performance starts to plateau. You see that it's flattening, whereas it should have just kept going linearly like that. And it's not going because of all these overheads. So we broke this down saying, okay, why is that happening? Whereas something is not speeding up as we add more GPUs. And when we break this down as, okay, are the matrix multiply slow? Is the all reduce slow? Is it some other whatever operators we saw? Which one is slow? So we see that the blue is the matrix multiplies. So the blue is actually scaling, roughly, you added double the GPUs, it halved roughly. Here also it kind of halved, it's fine. But the other blocks, like the adds, the all reduce, which is the green, the attention block, those are not speeding up as much when we add more and more GPUs. So at some point, it's not just the matrix multiplies, it's everything else that's in the decoder that is going to limit the performance. And that's, in a way, what's affecting GPU's performance. I think I see a question on the chat. Maybe, is there a question?
Yeah. So there are two actually. One was, I think, a little older question was about whether model execution time scales linearly with the number of parameters it's trained on. You may want to just clarify that. The second question is more related to, can LLM coder turn our idea into an app?
So I'll answer the first one first, and then the second one. So the first one, which is, does the execution time scale linearly? For the decoding step, where you're just streaming through the weights and KV caches, it does scale linearly. That is correct. Where assuming it's the same sequence length, which means the KV cache size is the same, and only the weights are different between two models, the execution time will be linearly different between the two. The one caveat there is if the model gets very small, the other things like synchronization, other things start affecting performance. For the second one, which is can LLM coder turn your idea into an app? That I'm not sure. I mean, I'm sure it can help you maybe, but I don't know, since I've not used it myself, I'm not sure of its capabilities. So
I have no further questions. Yeah.
Okay. So let me quickly flip through. Okay, so what have we done here? So Samba Nova has a new chip, which is effectively it's a training and an inference chip, and we call it the Reconfigurable Dataflow Unit, RDU. It's called Dataflow because it runs differently from some of the other architectures. So most architectures have instructions and data. So program executes by streaming a sequence of instructions through the chip. And as the instructions flow through, they have side effects. Like you change values in the register file, you load and store data from memory, perform computation, you update the value. That's how compute happens on a chip. On a data flow architecture, there are no instructions. So when you execute a program by pre-configuring the chip with a bunch of configuration bits, and these config bits explicitly identify what each unit in the chip is going to do. So once the units are configured to do a very specific task, data flows through them. And as data is flowing through them, they get transformed. Like they get manipulated. You add two things to produce one stream of output. That stream of output can be transposed, reshaped. And the end is that you get a final output. So it's a different paradigm of execution where it's almost like instruction flow happens in normal CPUs. Here, instructions are stationary, but data is flowing. So the key main thing is that's data flow. And the second is it has three types of memory. There's on-chip memory, there's HBM, and then there is off-chip DDR. This off-chip DDR part is not there in GPUs. And this was added specifically because model switching can become much better. So this is the same picture saying we have three tiers of memory. We need the on-chip SRAM because it helps with this flow of data, like this intermediate data has to be somewhere. The HBM is used for the same reason as GPUs. And DDR is used to keep all those models parameters. This helps us swap models in and out much faster than what's possible on other platforms. So very quick chip overview. So this is at a very high level. There are 4 tiles and there are 3 kinds of IOs. There's DDR in the dark brown, HBM in the light brown, and talking to other chips via P2P or peer-to-peer. When you run multiple multi-chip programs, these links get activated. So now we'll zoom into each one tile. So what does one tile have? It kind of looks like this. It's a 2-dimensional grid of memory, compute, and switches. So the memory is really the on-chip, like the SRAM that we have. Unlike a CPU and a GPU where there are caches, these memories do not have caches. So they're entirely software managed. What that means is if you want to use this memory, there is an explicit instruction to stream a tensor of data or a portion, like a tile of data from off-chip region to some on-chip memory, and then a separate instruction to start executing it. So there is no caches, no cache miss, etc. It simplifies the hardware. So this is the compute unit, where this is where all the matrix multiplies, the softmax, all those operations you saw in the decoder block, this is where they execute. So I'll keep it brief in that it consists of a series of pipeline stages. Each stage can be configured to execute one instruction. And this instruction is static. Once you configure it, it stays like that until you reconfigure it again. It can be used to perform a matrix multiply in a systolic array. such that all the ALUs are simultaneously occupied, or it can be a streaming unit. So we're doing things like a dot product, A plus B, A and B can come in on two different inputs. One of the ALUs can just keep adding it, and every cycle you can keep churning out a new output. All right. So this is the memory block. As I mentioned, there's no caches here, but it's not all memory. So it does have a whole bunch of logic around it, where most notably there is logic to produce addresses to the memory. So one of the more important things is if there is so much compute available on chip, something has to feed the compute. So to feed the compute, we need the required on-chip memory bandwidth. That's where all these PMUs come in. But to produce data at that speed, we have to produce addresses at that speed. So that's where we have ALUs that are solely built to accelerate address computation. So this happens all the time, where if you want to produce 64 elements per cycle, or 128 elements per cycle, or whatever it is, we have to produce addresses at that same rate. So that's why these ALU this box here is producing addresses. And there are alignment units here which helps accelerate things like transpose and other things like that. So let's skip over these. There are two kinds of networks where data is routed from unit to unit using something called the PLN, or the plasticine level network, where packets are routed from chip to one unit to another unit. These routes are controlled by software. So similarly, access to off-chip memory, which is the HBM, DDR, copying data to and from that to other units, that happens through units called AGCUs. It's called Address Generation and Coalescing Unit. That's how we end up accessing DDR, HBM, and CPU. Think of them as like little engines whose sole job is to copy tensors from one place to another place. So that was pretty quick, but let me just quick. So what did all that accomplish? If we go back to this picture, and this is a transformer, and we unpack this, and this is all the operators in that. Let me just go through two examples. Think, how do we execute these two operators on this chip? And then what do we gain from that? Let's just take matrix multiply as an example. So here the purpose here is C is a matrix. You want to produce this output from A times B. And the way we execute this is by loading a chunk of A, which is what is called a tile of A, into a PMU, another tile of B into another PMU, produce this output tile C into another PMU, and then store the result back to off-chip region. So in the data flow graph, this is what it looks like. Two AGCUs loading A and B tiles, a bunch of PCUs doing the matrix multiply. They all drain the results into a PMU. This PMU stores its result into another output via an AGCU. And in this spatial mapping, it kind of looks like this. Let's say you put A and B there. They route their data into that PCU. This PCU does the matrix multiply, produces the output there. If you want to do a parallel matrix multiply, we effectively expand this, saying, I'm going to put A's and B's in different PMUs now. I'll have to split A and B such that I have the bandwidth. And you feed the A's and B's across these the PLN, the interconnect, such that more PCUs are occupied. So now we'll go to an example of softmax. So in softmax, we have three operators. This is the it's a simplified version of softmax. It's not exactly right, but it really has three operations. There's an exponent, there is a summation, and there is a divide. Three ops. And there are some intermediate results here in the middle. So this executes where X is in a PMU originally. That goes to a PCU where the exponent is performed. The exponent's result is stored somewhere in another PMU. We stream M into a reduction. This reduction output is then sent to another divide here. And the divide's output goes to O. So this is how we'd execute softmax on the data flow architecture. So now, what if we are doing GEM and softmax and GEM? So let's say we are doing all of them together. As we saw earlier, you could cordon off a portion of the chip to do gems. So I'm showing two RDU solution, and then you can have softmax separately. All reduce can happen using these units in the middle, then another gem can happen here. So this is one, just to paint a high-level picture of how these things execute. This is how the fused operator can run multiple RDUs. All right. So now, let's tie this back into the performance for this model. So as I mentioned, GPUs perform this with multiple kernels, and there are overheads. Now, the good part with RDU is there are no more kernels in a single decoder. Because everything is data flow, you can partition the on-chip resources in one chip or in multiple chips, such that all these operators are simultaneously alive in a single kernel call. So no need to divide up the decoder into multiple pieces anymore. Everything is one kernel. It's what we call K0. So and this is just an automatic picture. So this is actually implemented, it's deployed commercially. And when we visualize what the PCUs and PMUs are doing, this is the auto-generated thing. But there is one more cool thing that happens here. Because all the decoders look like a single kernel, if you write this out as pseudocode, the pseudocode looks like this now. You see the same function executing again and again and again. Our compiler rewrites this. Instead of calling the same function 32 times, we rewrite this kernel such that this loop goes inside. There is a loop that runs 32 times, and the function just runs once. So this improves the overhead even more. Just to put things in perspective, what you see on the left is how the GPUs run it. Right? For all decoders, call 10 functions. Now, when we packed all of this into one decoder, that whole purple block became one line, it's just one kernel for us, just done it there. But it gets better, because we call the same function and again, we pattern match even more. And then, this entire loop disappears. Right. So because of all these optimizations, today, the SambaNova hardware we have is able to produce about 1100 or more than that tokens per second. This is in comparison with what we saw on GPUs, which is around 300. Yeah, so this is just the numbers. I think this is a snapshot, maybe it's a little older, but please feel free to try this yourself. Cloud.sambanova.ai, it's free. You may need to create an account, I think, but you can try this out. All these models are hosted, there's APIs and all that. So, but connecting this back to how did the performance improve? So we said GPUs didn't improve as there were more chips. What happened to RDUs? Well, we improved. So, from 8 to 16, first of all, 8 versus 8, you can see a significant bump. But as we add more sockets, we continue to see an improvement. The performance continues to scale with more number of hardware. And the reason, when we break this down, we can see that the synchronization overhead is basically gone. So all of these operators are scaling linearly. And this is just a simulation saying this black line is the maximum attainable HPM bandwidth. How much HPM bandwidth are we actually using as the time is going by? This orange line is showing that you're kind of close to the peak. There are some jagged edges here and there, but it's kind of close to the peak. Again, so this holds true when we batch as well. So normally you don't just deal with one request, you're dealing with a batch of requests where several independent users are asking something. The performance continues to scale with batching. And finally, one note on DRAM. So because we have the third tier of memory, if you notice, as more and more models are added, which is the number of 70 billion checkpoints, you continuously need more DGX boxes because you keep running out of HPM. But for RDUs, you don't actually need those many boxes because there's DDR. So there's a lot more capacity than GPUs. So this is the last word saying this data flow architecture is not just an inference product. I talk mostly about inference because that's the most that's the hot topic these days. But it is a training chip as well. It is competitive with in terms of teraflops and pretty much everything else with H100. And it's when we do this with all the advantages I described with Fusion and Dataflow, you can actually train about 2 to 3, sometimes 6 times faster than GPUs. Right. So with that, this is my last slide, and I'm happy to take any more questions. If you want to just try this out, say what does 1,000 tokens per second feel like? Please go to this website, cloud.sampanova. You can try this variety of models there. Everything I have talked about in this slide deck are part of 2 papers. One of them is published at a conference called Micro that happened last November. And another one is on arXiv. So please feel free to download them, and there's a lot more detail in there. Okay, with that, I think that's my last slide. I can stop here and pause for questions.
Thanks, Raghu, for a very insightful presentation. I had one question, and then I'll read one question from the attendees. From what I gathered, from the data flow architecture, what I understand, and maybe correct me if I'm wrong, my takeaway was that there were in the GPU architecture, there are multiple kernels for specific instruction sets, and in the data flow architecture, you combined all those specific instructions sets into your chip itself, because these are commonly occurring or repeated instruction sets which have already been which are now coded into the hardware itself, and then only the data flow has to change, and the sets of instructions are pretty much the sequence, and the set of instructions are constant for the training as well as for testing. So you're able to achieve significant boost in the performance. Is that a good way to look at it, or am I missing something fundamental?
I think it's a concept at a high level, it's right. But one clarification is the instructions aren't really baked in that way. The units themselves are pretty configurable. As in
So the architecture and softmax that you were talking about, they're not baked in, right? They can be configured.
Correct.
Okay.
Correct.
I see.
So the slides was just showing an example of one way to map it. It's possible to use other PCUs, like spread it out over more than one PCU. So that's a mapping decision for the software, where software has the freedom to allocate more or less resources depending on what else is going on chip. And the key thing is when more than one operator is simultaneously mapped onto the same sort of RDU, sort of the grid, because you have all these PMUs and each PMU has all this addressing flexibility, these multiple operators, they can have any kind of access pattern. Like your matrix multiply might produce things in reverse because that might be the best way. You might need to do a transpose, which means you have to access things in a different way. And then you might have to do a softmax on some other tensor axis. All of this is possible because of the flexibility. Doing this can get a little difficult on things like GPUs.
All right. Okay, thanks. Thanks for the clarification. Yeah. There's one question from the attendee. It's more on the target model architecture. Does the draft target model architecture reduce time complexity rather than only using the target model? I think you answered this, but you may want to just clarify it one more time, please.
Yeah. It does reduce the time because so one way to think about it is if you look at the big O notation, let's say that to produce one token, target model takes order of t, say O of t, to produce one token. If you want to produce n number of tokens, it will be n times O of t. That's the time complexity for the target model. If you want to produce the same n number of tokens using draft plus target, you will be producing n divided by k. That's the number of steps you'll have. And for each step, you'll have k times O of draft plus 1 O of n, 1 O of target. And the draft model, the O of D, which is the draft model, is almost about 10 to 20 times lesser. So if we go back to this slide here, what you see here, like 1B, 3B, 8B, these are the speeds of the draft model, 2500, etc. This is the target model with speculative decoding. So without speculative decoding, 70B is probably going to be around 150. So if I compare it roughly, 150 versus 1500, it's about a 10x gap.
Great, thanks. So there's one question which around what are the computational characteristics of the workloads that make this data flow architecture run more efficiently than the conventional GPUs? Is there anything correlated with sparsity or high memory footprint related to ML training? Is there anything connected to that? And an added question to that is, are there any applications which will not benefit from running on a data flow kind of an architecture versus a GPU?
Right. So the first one is, okay, what helps? Why is data flow architecture better here? So one is the regularity. So if it's when I say regularity, I mean there's regularity in control. So even if it's sparse, the flow of data is deterministic. So in other words, these operators have, you keep switching between like the compute bound matrix multiply, then the bandwidth bound softmax, then back to compute bound. These might need to operate in different precisions. The fundamental thing between any GPU or RDU or any other architecture is when you fuse multiple operators together, it enables utilizing the chip resources better. The challenge with fusion is all these intermediate results need to be managed somehow. Like we need the space on chip to put it, and then we need the flexibility on chip to access it in whatever way we want. And usually that managing those intermediate results becomes very difficult on GPUs. And because the flexibility, because we have more SRAM, we have the interconnect, the ALUs and the PMU and all that, managing those intermediate results and traffic becomes easier. And that's what helps data flow gain this much utilization. So we avoid all the round trips back to HBM because everything is on chip. Where data flow doesn't shine, so where do we not do well? I think one of the places would be something where it's like very control heavy. So this is something where even GPUs probably won't do very well. So for example, think of like a control loop. So it's very it's rife with if then else statement, where every single time you're branching and the branch is data dependent, for example. This is where a traditional instruction-based architecture does very well. Like that's what it has been built for and optimized for with branch predictors. If there is some locality in the way you take a branch, it's there's all the machinery there. So if the workload looks like that, a CPU style architecture is better. If the workload looks like something where you can parallelize things, then data flow architectures can exploit that.
Thanks, Raghu. I don't think there are any further questions, and we also passed the time. So again, thank you very much, Raghu, for being part of this very first session of 2025. We will have many more such interesting sessions lined up in the coming weeks and months. And thanks for kickstarting 2025 with a wonderful session, and we really enjoyed. I think many of us who don't have a hardware background, I think for us it was an eye opener to see how a GPU and how a data flow architecture looks like. So thanks for articulating these ideas in a manner that is easy to understand for most of us who attended today's talk. Thank you again, and to all the attendees, have a wonderful day.
Yeah, my pleasure. Thanks a lot for having me. Thank you all.
Thank you, everyone.
Bye.